I always seem to forget to bring the chat up before I start the recording. There we go. All right, so welcome back. We're going to do one more problem in differential equations today, and then that'll actually wrap up our entire differential equations discussion. So, like I mentioned, just kind of scratching the surface of this huge field, but that should give you a feel for some of the basic topics in DiffEq, and also hopefully give you something to either provide more insight into some previous experiences with maybe engineering or physics or chemistry courses, or bring to those courses for either that you're in currently or in the future, um, and give a little more insight and depth into some of the formulas and theorems and things in those courses. And then we're kind of shifting gears again. Calc 2 can feel a bit like a motley assortment of topics sometimes, but shifting gears again to chapter 10, parametric equations. I did already post a supplement on chapter 10, so I don't know if we'll quite make it up to the material where that supplement picks up or not today, but that supplement's available on YouTube in the supplemental material folder. So take a look at that supplement. And then of course, this will be posted this lecture will be posted in the standard uh, Calc 2 lecture folder. The quote of the day today, I think we've had this quote already this semester, but I think it's also a good one around this time just to remind ourselves of. It's one of my favorite from my favorite grad school professor, Professor Layton. Good decisions come with experience, and experience comes from making bad decisions. And around midterm time, you get midterm exam grades. Uh, we haven't quite had the midterm exam this week in this course, but in other courses, you might have had midterm exam or other exams already. You might be at a point in the semester where you're looking back and some things have gone really well and some things maybe have not gone so great. Um, and you can either just kind of, plod forward with the same mentality as the first half of the course, or you could look back and you could say, okay, this or that thing maybe didn't go so great in the first half of the course. What can I change in the second half of the course that can maybe make the next exam or the next whatever it may be, the next project, the next paper go a little better? Can I prepare a little bit better? Can I prepare differently? Can I, go to a tutor or something to study for an exam, or reach out earlier if I struggle with something, pop in office hours, anything like that. Um, so, maybe do you need a little bit more direction to your studying? Would it have been better for you to have studied, say, more high yield topics? Or are you the type of person who, like me, spends all of your time pointing yourself in the right direction? And it's like, okay, I procrastinated a little too long on getting started with the studying. I need to just get started and then kind of find my way a little better as I move along the path. So I think this is a good point in the semester just to kind of take a look at that, look backwards. What are some things you wish you could have done differently? Look forwards. Can you make that change for the second half of the semester? In most courses, there's still plenty of time to bring a grade up to, pretty much whatever grade you want for the most part. Okay, and then just a reminder, the midterm exam is this week. It was available this morning, I suppose, at 9 a.m. I almost said yesterday, I don't know. uh, it's only been half a day into the week and it already feels like a full day. Through 11:59 p.m. this coming Sunday. The material is chapters 6 through 9. And as I said here, kind of implicitly 1 through 5 as well. Sorry, with the warm weather, my allergies are bonkers these days. Um, so implicitly chapters 1 through 5, the Calc 1 material, of course. Um, and as I mentioned last time, there will be a bonus problem from chapter 17 from the second order differential equations material. So, if you want to throw that on into the studying as well, probably not a bad idea. You can get some bonus points there. And those can be bonus points that kind of fill in a gap that if you miss another problem. But if you get more than 100% on the exam, then that does count towards your grade. So it's not like your exam grade is capped at 100%. If you get, whatever 110% or something, then you have 10% of that, whatever percentage the midterm exam is. I think it's 30%. So you have 3 extra percentage points going onto your final course grade that could offset, maybe a final exam that's a few points lower than you want, or some homework points or something like that. And the sample exam is posted. So that should be available for you to take. And the biggest thing is I strongly recommend planning to take the exam on or before Thursday night. That way, if anything goes wrong, you have some buffer. There are no due date extensions on the exams. So homework, due date extension is not a problem, but exams, there are no due date extensions. So give yourself plenty of time to take the exam and to find, solutions if any problem arises. Okay, so with all of that being said, let's look at our last little bit of chapter 17. So last time we kind of set up the theoretical background for case 3 to distinct complex roots. Here we're going to remind ourselves of that, and we're just going to work through one problem. I decided I think one problem is sufficient for this. This is just kind of a scratching the surface. After all, we're not looking to go super deep into any of this material. Okay, so recall that we have our second order differential equation we've been working with, second order linear. So the only place in each term, we only see y or one of its derivatives to a first power. No sine of y's, no like y squareds, no like y times y primes. So linear, homogeneous, meaning we have an equal 0 on the right-hand side here. Constant coefficient, meaning these a's, b's, and c's are not functions of the independent variable. We only have the dependent variable explicitly shown here. Second order ODE. So lots of adjectives, but in the context of differential equations, usually the more adjectives, the better, because you're kind of cutting down the breadth of the types of equations you're looking at. But even with all of these adjectives, even with this kind of significantly restrained view of second order equations, this actually covers a lot of different models. RLC circuits, Newton's equations in a lot of scenarios, mass spring system, which we saw, in some sense, kind of the pendulum equation. It can be approximated as basically a mass spring system for small angles of deviation. There are a lot of systems that can be modeled very well by this type of differential equation. This has characteristic equation AR squared plus BR plus C equals 0. We got that by trying e to the RT as a solution. And as we discussed last time, we have 3 cases, one of which where our discriminant is negative, we get complex roots. We have to make sense of what does e to the I theta mean. And again, that was part of the discussion last time. And here we have roots with real part alpha equals negative b over 2a, and imaginary part beta equals the square root of negative discriminant over 2a. And we worked our way to the general solution, which is constant e to the alpha t cos beta t, plus another constant e to the alpha t sine beta t. And that was our general solution. Let's apply this work to this initial value problem. We'll first solve the differential equation. We'll get a general solution, a family of functions parameterized by C1 and C2 that solve this equation. And then we'll pluck out the single member of that family of functions that has what we might say is something like an initial position of 0. If we're thinking of, say, a mass spring system, maybe this is initial position at equilibrium where the spring isn't stretched or compressed, but with an initial velocity of 9. We're kind of giving it a whack, 9 units of velocity in the positive direction. We actually can kind of think of this as a mass spring system here because we note that all of the coefficients are positive. So this is kind of a sensible model for a physical system like a mass spring system. And we can kind of imagine what we think a mass spring system should look like in the presence of air resistance or drag. And we can see if the answer we get makes sense with such a system. Okay. So let's start by looking at our characteristic equation. We get r squared plus r plus 37 fourths equals 0. this tells me my discriminant is, well, it's b squared minus 4ac, or it's 1 squared minus 4 times 1 times c is 37, or 37 fourths. The fours go away. We get 1 minus 37 is negative 36. Discriminant's less than 0. This is going to give me two distinct complex roots for r. So we are in case 3 here, as would be suggested by the location of this example. Oops, went a little too far there. There we go. So now let me take a look back up here and take a look at alpha and beta, figure out what each of those are. Alpha is negative b over 2a, or negative 1 over 2 times 1, negative 1/2. And beta, well, what's beta? It's square root of negative d, we could write it that way, over 2a, or it's the square root of 36 over 2 times 1. Well, that's just 6 over 2, or 3. So I get alpha is negative 1/2, beta is 3. And I can plug these in to get a general solution, y equals c1 e to the negative t over 2 cos 3t plus c2 e to the negative t over 2 over 2 sine 3t. And this does look like something that we'd expect from the physical system. This is a family of functions. We do see we could, if we wanted to rewrite this, we could do e to the negative t over 2. Then I have one number cos of 3t plus another number sine of 3t. With a little bit of trig, that turns out to be just an amplitude. Let's just say sine of 3t plus a phase angle. So I have oscillations that die out. I have something that looks like this. Exactly what we would physically expect with a mass spring system with a damping term, where there's air resistance or friction present. Every time that the mass moves from one side to the other, it gets a little more of its energy sapped, distributed in the system as maybe heat or maybe sound or something like that, and has a little bit less to keep in motion. Okay, so this is the family of functions that solves the differential equation. Which which member of this family of functions? I'm just having a heck of a time selecting things today. Satisfies both of these initial values. So I know that on one hand, y of 0 has to be, well, that's c1, e to the 0 is 1, cos of 0 is 1. But then my second term, sine of 0 is just 0, so that goes away. So for my family of functions, y of 0 is c1 for every member of this family. And for my initial condition, y of 0 has to be 0. That's my initial condition. So c1 must be 0. So now I have kind of an updated family of functions. C1 has to be 0, so now the only functions under consideration are C2, e to the negative t over 2, sine of 3t. This is kind of my revised search space, I guess you could call it. These are the family of functions these are the members of the family of functions that satisfy y of 0 equals 0. Which one of these satisfies y prime of 0 equals 9? Well, let's find y prime. Here we'll find y prime of t first. What can I do? I differentiate the first. I get negative 1/2 e to the negative t over 2 sine 3t. And then I differentiate the second, write it underneath here, plus So I differentiate sine to cosine. It's going to give me plus 3 C2 e to the negative t over 2 cos 3t. And then I need to know something about y prime of 0. That should be 9. So y prime of 0 from my model, well, the first term, I get a sine of 0, that goes away. So it's got to be 3 C2, e to the 0 is 1, cos of 0 is 1. So it's just 3 C2. And then again, for my initial condition, that had better be 9. So my initial condition says this has to be 9. My model says y prime of 0 is 3 C2 for any function that looks like that. And my initial condition says set that equal to 9. C2 must be 3. And I have, after all this shakes out, I have y equals 3 e to the negative t over 2 sine of 3t, exactly what I'd expect. I note that it does, this exponential function is positive, so this is going to look like sine of 3t, meaning it's going to go through 0, 0 and start going up in the positive direction, but it's going to be immediately kind of attenuated in a sense by that exponential decay. Something like this. So we do have this kind of initial position of 0 and a sharp, amount of energy making an initial positive velocity going in the positive direction this way. And then the kind of mass spring system takes over from there. The spring gets stretched out from that initial oomph, and then it wants to compress. So it compresses, pulls back to equilibrium, but overshoots a little bit. The friction or air resistance isn't so much that it saps so much energy that it can't overshoot. It does overshoot. And then the spring compresses, pushes it back, it overshoots again, keeps going back and forth, but those oscillations do die out. So it's what we would expect from a system that might be modeled with something like this. Now remember, in our previous couple of cases, we were looking at differential equations where we might have had a negative coefficient here or there, and a negative coefficient on the Hooke's law term or the air resistance term doesn't make a lot of sense from something like a mass spring system or a pendulum or something like that. So there we wouldn't have been able to so tightly tie the solution to something that would make sense physically. So we don't want to, take this too far, but I was using this as a good example because I noticed that I had all positive coefficients here. So I can really interpret this as like a model for a mass spring system. And that gives me some gut feeling intuition to go along with the mathematics. All right. So with this problem being done, any questions on differential equations? If this seems like a fun topic to you, you can take DiffEQ. Calc 2 is the prereq for it, so you can take it in the either the summer or fall if you're interested in it. It's I think it's probably my favorite course to teach, even though I haven't taught it in a couple years at this point, but probably my favorite course to teach, DiffEQ. Okay, so moving on to chapter 10 now. So chapter 10, parametric equations, parametric functions. So starting with 10.1, just introducing what are parametric equations? What are the basic ideas here? So I might think of a situation where I have, say, x and y, and I have some function describing their relationship. Something like y equals f of x. Maybe some trig function or something like that. This looks like it might be a trig function shifted up a little bit. And in a lot of situations, this does a really great job of describing whatever phenomenon we want to describe. So in particular, I might think of like, y as a function of t up here, and that works pretty nicely. I have one dimension of motion, one spatial dimension, one time dimension, works nicely. But I might think of like maybe y and x being maybe two spatial dimensions. So I can say when my particle that's maybe somewhere on this line is here in the x direction, when my particle is located here, this is its y position. And when my particle is located here, this is its y position. But if I imagine a particle in two dimensions, maybe like a ball rolling around on a table or something like that, well, there's no real reason that I couldn't have, why can't the ball do something like this? If x and y were spatial dimensions, I mean, this would be a perfectly reasonable path that if the ball was laying on a table, it can make a loop and, it could do that. That's not a problem. So if I'm thinking of something like this scenario where x and y are spatial dimensions, and I have a ball rolling around on the table, I don't really want to be constrained by things like the vertical line test and worrying about whether things are functions and so on. But I need to get some kind of functional idea out of here. I really want to build up to the point where I can use all of the algebra of functions and the calculus of functions, everything that I've built up to this point in mathematics. I want to bring that to bear on this problem. I don't want to just start fresh with some completely new idea. So where's the functional relationship here, right? It's not between x and y. If I'm here in the x position, I could be here or here or here in y. It's no longer, there's no longer a direct, nice functional relationship between x and y. But really, if I imagine this ball rolling on a table, the inherent functional relationship is with time relative to space. So I can say at time one, some time that I choose to call time one, my ball was here at this x position and this y position. At time two, my ball was here at this xy position. At time maybe three, it was at the same x position but a different y position. That's perfectly fine. Right? It could be at time five has the same maybe y position as time two, but a different x position. Time three and time two have the same x position, but different y. In fact, I could even be at the exact same xy location at two different times, as maybe time 2.1 or something, I end up there, and maybe a time like 4.2, I end up there. I note that this black curve here represents kind of a curve that I'm traversing in a certain direction over time. So if I wanted to model, say, two spatial dimensions, x and y, and the path that something takes through that over time, I might model it this way. Or even if I want to abstract away from that, and I can say, what if I just have this curve in space that I want to describe in some way in xy? I just drew this curve in the xy coordinate plane and I want to describe it. It's going to be a huge pain to describe it with something like y as a function of x as like piecewise functions, or even as an implicit relation between x and y, like, circles and ellipses are not proper functions, but they have kind of a relationship like x squared plus y squared equals r squared or something like that. But even something like that seems like it's, not likely to be able to describe this type of a curve well. So even if I'm not thinking of x and y as spatial and having a time dimension, I could just ask the question, if I have this curve in 2D space that's not necessarily a nice functional relationship, is there another way I could describe it? And the answer is yes. We call these parametric equations because I kind of have, instead of a situation where I have x and the knowledge of x uniquely determines y, that's not the situation I'm in anymore. I have some freedom between x and y. but it's not complete freedom. It's not like if I choose, what color haven't I used? Blue. It's not like if I choose this value for X, I can choose any value for Y and those are permissible values. No, I mean I have more than one, but I do have a constraint on the Y's that are available. Right, there is some constraint that I'm trying to stick to this one-dimensional curve here. And that's where my parameter T comes in. So here, when T is a certain number or a different number or yet another number, the number that T is gives rise to both the X and the Y coordinate. So X and Y are certainly related. It's not just like X is completely arbitrary and Y is also completely arbitrary. It's really that kind of T is arbitrary and it determines what X and Y are. So X and Y are still kind of related to one another, but they're related through this parameter T. We quite often call it T because we quite often are modeling space as space or dimension as a function of time. But this doesn't necessarily have to be time. Often it's something like angle. If we think of a circle, we might choose to parameterize that circle in terms of the angle with the positive x-axis, giving rise to an x and a y coordinate along that circle. So often we call it t, doesn't always have to be t, and doesn't always have to be time. Now, it is important that x is actually a function of time and or of t. I probably will call it time. I should just call it t, but I'll probably call it time because it just feels so natural. But it is important that x is a function of t and y is a function of t, as in legitimate functions. So in other words, I can't have t equals 5 here and also t equals 5 here. That's not allowed. At time 5, the ball has to be in one place. It can't be in two different places. So each choice for t results in a specific x and a y. But these aren't necessarily one-to-one functions. I could get the same x occurring at different t's, or the same y at different t's, or even the same xy pair at different t's. If I just gave you a snapshot and showed you that the ball was at location, the red point there on the table, and I asked you what time was this, is it 2.1 or 4.2? you want to be able to answer. But if I told you the time is 2.1, where's the ball, you could point to the red location and say, there it is. Okay, so, oh, and then one last thing is that if we have a nice function of x in terms of y, there's nothing saying we can't choose to do this to our nice function. We could choose to parameterize a nice function. This might be a nice y equals f of x, maybe like a cubic or something in this case. I could certainly choose to reframe this as x equals x of t and y equals y of t. I mean, the simplest such example would just be something like x equals t and then y equals f of t. But I could choose a different choice for x and get a different output for y as well. Okay, so let's take a look at something along the lines of a quote nice function like this, y equals f of x. What if I had written something like a nice function, a nice relation directly between x and y? What if I had it written as a parametric equation? When I'm looking at parametric equations like, say, these ones, they can be a little bit hard to wrap my head around how to graph it. If I wanted to say, can you plot the curve that represents the path of, let's say, this particle, the xy path over time t? It might be a little bit hard for me to do that. Maybe this one is recognizable enough that you think you can do it, but there actually is a little bit of a hitch here even. But we're much more adept at recognizing things like y equals x squared or y equals square root of x. We're much more used to looking at direct relationships between x and y and knowing what the how the algebraic structures relate to the graphical representations. We're much better at that. Sometimes it can be useful to eliminate the parameter, particularly to get a graph of the path. Let's try to do that. So what I have here is a parametric equation or a parametric function written like this. My goal is to kind of rewrite it just as a direct relationship between x and y. Now, when I do that, I lose the information about t. If I was thinking of an actual ball moving around on a table, I lose the information about where it is at time t, but I can draw the path much more easily. And then maybe I can reverse back into it and figure out how the t information fits back in. So how can I eliminate the parameter here? My goal is I have 3 degrees of freedom in a sense. I have t, x, and y, and I have 2 constraints. Can I bring that down to 2 degrees of freedom, just x and y, and 1 constraint, one equation relating them? If this was a simpler equation, I might be able to solve both explicitly for t and then set the t's equal to one another and relate them that way. But I don't really want to end up with arc cosines and arc sines and all of that here. Is there anything else I can do? I could think of like linear equation solving methods, but these are nonlinear functions, so that's maybe not going to work so well. But if I get a little bit creative, I might realize that, hey, wait, sine squared t plus cos squared t equals 1, and 1 doesn't have any t's in it. So if I look at x squared plus y squared, what does that give me? That gives me a squared sine squared t plus a squared cos squared t, or that's just a squared on the right. So I see that this parametric function is tracing out a curve that looks like just a circle of radius a. X squared plus y squared equals a squared. Now, depending on the domain for t, depending on how many t's I plug in, this might trace out the whole circle. It might trace out part of it, maybe just like the first quadrant or something. It might trace out the whole circle multiple times. So there are some nuances here that I haven't figured out, but I can graph this pretty easily. So as my ball moves around in time, it's got to be somewhere on this circular path at all times. Now, I have lost in this picture the information about t. So we'll kind of come back to that a little bit later. But since I have lost the information about t, I do have to be aware of that, right? If I am actually modeling a physical object rolling around, if I don't just want to graph, I might also be interested in like, at t equals 0, say x equals 0, y equals a. I might be interested in the fact that at t equals 0, I'm at that point, x equals 0, y equals a. So this isn't really the parameterization of a circle that we're used to, where we kind of start at the positive x-axis. Here we're kind of starting on the positive y-axis. We might have noticed that we might have expected that because we have x and y associated with sine and cosine respectively, but that's kind of flip-flopped from what we usually think of. We usually think of x being associated with cosine and y with sine. Or I know that when t increases a little bit, if I write t equals 0 plus, if t is just a little bit bigger than 0, then sine is going to be just a little bit positive. Here, and let's say a is bigger than 0 here. Let's just assume sine is going to be a little bit positive, so x is going to be just a little above 0. And then cosine is going to be just a little below 1. So I'm going to write a minus, just a little bit below a for y. So I'm going down and to the right a little bit. I'm actually traversing the circle this direction. I'm actually traversing it clockwise. If I had a certain domain for t, say t between 0 and pi, or 0 between 0 and 2 pi, or between 5 and 10, I might be able to investigate, do I actually trace out this entire circle, or do I only have a segment of the circle that I trace out for a given interval of t? Okay, let's look at another example here. So this is the projectile motion parametric equation. And here v naught is initial velocity, h naught is initial height, and theta is the angle of elevation. So the idea here is we have the ground at y equals 0. We have our, say, cannon shooting a cannonball. It has initial height, h naught. It's shooting with velocity, or it's shooting in a velocity with speed, v naught, at angle theta, inclined from horizontal. And the question is, the path of this cannonball, neglecting air resistance, what does it look like? We can model x and y separately. We can first split our velocity into its horizontal and vertical components, v naught cos theta and v naught sine theta. So we're moving horizontally at speed, v naught cos theta, and distance equals rate times time. So our horizontal position, x at time t, is going to be our speed, v naught cos theta, times the time it's been going that speed, times t. What's our vertical position? It has a similar v naught sine theta times t, coming in linearly in t. It started at a height h naught, so that was its initial height. And then it has this minus 16t squared, obviously from the influence of gravity. That's negative 32 over 2. It's negative because gravity is pulling it down in the negative y direction. And 32, what is it, feet per second squared is gravity, the acceleration due to gravity. So this is negative g over 2 t squared. And I'm using feet just to annoy all of the other people in the sciences. I'm actually using feet because 16 is a nicer number to use than whatever 9.8 over 2 ends up being. So this is our projectile motion equation. What kind of a path does this describe? Does it, if I eliminate the parameter, does it describe a path that I can easily recognize, maybe graph, maybe know something about? Or does it represent some kind of wonky path that, that I don't really know what the path is going to look like? Well, let's see. In this case, we actually have a pretty nice setup for x in terms of t, not like up here where we would have to do like arcsine or arccosine to solve one for the other. I actually can just solve this first equation, which I don't know why I can't select anything these days, but I can solve this first equation for t. Remember that theta is actually a constant here. I know it looks a little funny because a lot of times we think of theta being a variable, and we will again in a second here, but in this case, theta is a constant. So I can actually solve x equals number times t for t in terms of x over number. So t is x over v naught cos theta. Then I can just plug that in for y. And then t squared is going to be x squared over v naught squared cos squared theta plus v naught sine theta over v naught cos theta. That's actually just tangent theta. That actually kind of feels right. It's like shooting off at that tangent. This line here should be tangent to the path. Tangent theta times x, and then plus h naught. Hey, I just get a quadratic and just get y equals number x squared. Well, let me actually write something algebraically valid. Ax squared plus tan theta x plus c. We just get a quadratic path, just a quadratic opening downwards. We see our linear term, tan theta here, actually kind of meshes with what we might expect. And a turns out to be this. All this stuff here, negative 16 over v naught squared cos squared theta, just some big constant. And then c, just our initial height. That also makes sense. Okay, let's look at graphing something like this. So here I have x of theta equals theta minus sine theta, y of theta equals 1 minus cos theta. Now I might look at this and I might say, well, can I do the trick like I just did? Can I solve one of these for theta in terms of the other and get a nice function out, nice relationship between x and y? Not really, right? I mean, I can't solve this one for theta at all. It's a transcendental equation. This one I could, but I'm going to get in theta equals arc cosine of a bunch of stuff, and plugging that in here is not going to help very much at all. Can I do this kind of a trick? Can I do like x squared plus y squared, or even if this was just a constant, I could do like y minus 1 squared would be like cos squared theta. That would kind of work, but here I'd have to do like x minus theta squared equals sine theta, but that doesn't, the fact that theta is both inside of the sine and outside of the sine in the x equation really throws a wrench into things. This is going to be an example where I don't want to eliminate the parameter. If I was going to graph this, I might just kind of start thinking about what the graph might look like. And then I might actually just jump over to my calculator and have the calculator help me out with this one. So let's give a little bit of thought to what this might look like. Here. So what is y going to look like in terms of theta? So as theta goes from, well, I see y is going to be 2 pi periodic. X isn't quite going to be, but so y is going to be 2 pi periodic. And I'm looking at 1 minus cos theta. So when theta is 0, y is 0. And when theta is 2 pi, cos of 2 pi is 1. 1 minus 1 is 0. And I see that I have y is 1 minus cos theta. So when theta is, let's say, pi, cos of pi is -1. That's 1 plus 1 is 2. So this is like, we can think of this as like minus cos theta. So flip cos theta about the horizontal axis, in this case, the theta axis, and then add 1, shift it up 1. So I think it's actually going to look a bit like this, almost kind of like a bell curve kind of situation. But y is going to kind of start at 0 height, go up to 2, and then come back down. What is x going to do as a function of theta? I'm actually going to kind of write it a little bit funky here. I'm going to write it as like x as a function of theta, so that as theta evolves, we can see how x traverses left to right. So here's theta. Here's, let's say, 2 pi and maybe 4 pi. So x is theta minus sine theta. If I forget about the minus sine theta, x equals theta looks like this. And then to that, I want to add a negative sine theta. So I think it's going to do something like that. Maybe a little more extreme on the wiggles, but I might wiggle a little bit more sharply than I kind of drew it there, but something along those lines. So x is going to more or less kind of keep getting bigger in that direction. I don't think it should ever go back left, even though it looks like it does there for a second. But, so x is going to keep getting bigger kind of in this direction. All right. So for me to combine these two together, it's not going to work nicely algebraically. It's not going to work super nicely graphically, but I see that my y should be cyclic and my x should be kind of traversing over time or over theta. Let me change my share here really quick. My screen share, get the calculator brought up. Oh, hit the wrong thing there. Okay. All right, so let's look at the calculator. We don't need that. So I want to graph this parametric equation directly. Right? I don't, it's not reasonable for me to solve it for y in terms of x. If I go to my y equals menu, obviously my screen is set up for y in terms of x. Now, if I go down here to mode, see next to second, next to the yellow button, there's a button for mode. I'm going to be doing these demos on the 83. It should work basically the same whether you have an 83 or 84 or anything like that. If you have a different calculator, it might work a little differently. So you might have to either Google or look up YouTube videos on your calculator, or of course, you can always pop in office hours and I'm happy to help with whatever calculator it is. But in class, we'll use the 83/84 setup as the demo. So if we go to mode here, you notice there's a bunch of options here. We can change how many floating points we want. We can change radian or degree. We better be in radian if we have an angle outside of a trig function. And this one here might be one that you didn't really use before. Maybe you used polar, I don't know. But we see right now it's on function, kind of the standard. If we go to the right one, PAR, that stands for parametric. Let's hit enter there and make sure that that's selected. And that looks good. Leave everything else all to the left, but we've switched to parametric. So that's under mode. next to the second, the yellow key. So mode, and we see that we're in parametric equation mode. So now we go up to y equals. See each of these slashes on the left here? Each new slash is a new function. So we have one slash that's associated with x1 of t and y1 of t. Another slash that's associated with x2 of t and y2 of t, and so on. Our variable key actually is t. When I hit this xt theta n, instead of using x here, which would be our kind of functional variable that the calculator will use, it'll use t because it's thinking in terms of parametric equation. Just a little bit, there would be nothing wrong with it calling the variable x, but we usually use x and y as our position variables, and then something like t or theta as the parameter. So let me go ahead and type this in, and here I'll use t instead of theta, just because that's the way the calculator wants it. So x is going to be theta minus sine theta, or t minus sine t, and y 1 minus cos t. If I go over to window, I need to choose x and y for the window that it's going to display, but I also need to choose a t value, or a t interval. I know that let's start with y. I was doing some examples for another class on this, so that's why there are such big numbers in here. I think that y is going to be between 0 and 2. Let me go maybe from like -1 up to 3 in y, just to make sure that there's nothing kind of popping off of the screen that I didn't think would be there, but that ends up being there that I don't see. I also think that y is going to be 2 pi periodic, and I think x is not going to be. Maybe I'll go from like 0 to 4 pi on theta, or in this case on t. By default, the calculator gives me 0 to 2 pi, but I'll put 4 pi in here. So 4 pi, and it figures out that's 12.5 or so. This t step, I never really change it. If you want to put it somewhere around 0.1, if yours has been changed in the past, that's probably a good t step. This is just like when I was drawing these points up here, these green points. Obviously, the way the calculator is drawing these pictures is it picks a bunch of different t's as inputs, gets the xy point as output, and just plots those going along. So the smaller your t step, the more kind of refined the picture will be, but also the longer it will take to graph. I think 0.1 is usually, that's just what it comes at, and that usually is good enough for most things. And then I kind of expect that x, which on one hand, if I forget about the sine theta, just looks like x of theta equals theta. So going from something like 0 to 4 pi. Now, what's the effect of the minus sine theta? Well, I think that when I'm at 4 pi, the sine theta is back to 0 again. So I think if I let theta go from 0 to 4 pi, letting x go from 0 to 4 pi probably will work as well. And let me graph this. I do get this cyclic nature in y. I see 2, 0 up back to 0 cycles in y. I see that x does kind of just progress left to right. It's not doing something like, right? It's not doing something like this. Right? It's not like x is going left and right wildly as y is going up and down. And I kind of expect that if I were to expand my window to maybe like 6 pi, I'd probably just get another one of these little arches. Kind of want some McDonald's fries right now. So do I get 3 arches? That would be my prediction. And I do. So I'm pretty confident that I understand how this graph works, even though it can't be written nicely, y is a function of x. It actually does look like y is really a function of x. If I tell you what x position I'm at, I can tell you exactly what y you're at that point. And I can even tell you exactly what theta you're at as well. So I have this kind of a setup. If I want to get the perspective right, I can go to zoom and then zoom square, number 5 here, zoom 5. We'll kind of square things up so that the perspective is right, because we set a certain horizontal and vertical, set of choices based on just what we knew would make it fit in the screen properly. But that can distort the image, right? So we see that actually these curves are a bit flatter than we maybe initially thought. Whenever the axes, the x and y limits, are set to match the kind of aspect ratio of the TI screen. And it turns out this is what's called a cycloid. It's a function of y in terms of x, even though it doesn't have a nice way to write y equals f of x. It is a function of x. And the way that you would get something like this is if you actually took like a bicycle. I don't think this is what a bicycle looks like, but and you look at bicycle wheels, and if you put maybe I'll make it red. If you put a little light on here that's emitting some light, and you pedal the bicycle forward, the path that this light will take, it'll take a little while for it to get to the top of the wheel. I kind of overshot there a little bit, and then it'll be back on the ground, and then a little while later, it'll be at the top of the wheel again, and so on. That's the path that this light will take on the edge of a wheel. Kind of interestingly, you can ask what happens if I attach the light to a spoke, maybe like halfway between the ground and the point of rotation of the wheel. What would it look like then? Would it look like this? Probably not. And actually, that might be an interesting question to ask and to think about, to either look up the answer to or try to like work out the answer to. Or it'll be interesting to try to work out why is it that if I kind of follow this circle around, if I follow a point on the circle around as it rolls without slipping, I get this cycloid. So we'll leave that kind of as an exercise to investigate those different ideas. Either to investigate them yourself, or I know this is kind of midterm exam week, so a lot going on this week. If you just want to Google it or something, you can, I'm sure, find a really good 10, 15-minute YouTube video on it where this can be explained as well. So, but give it a little bit of thought. I would say, at least take 10, 15 minutes and try to work it out yourself, why following that edge of a circle should result in a curve like this that's described by this equation. All right. Let me stop the recording.